Morning, everyone. My name is Bharadwaj. I'm presenting work that was done by several engineers at NetApp that's summarized in this paper titled I/O in a Flash. This is a deployed system. So all of the stuff that I'm going to talk about is already in products that are being sold by NetApp, and they have been for a few years. And this is being published after the fact. I'll get straight into it. So about a decade or so ago is when Flash arrived in the data center, and it brought an exciting step change to the business of storage systems. And at that time, we saw the industry at large set about building systems from the ground up to suit the device characteristics and economics of SSDs. Right? At that time, roughly 10, 11 years ago, ONTAP was already a 20-year-old system. And it had been built over that time into being an extremely feature-rich, extremely reliable system that was loved by enterprise customers. But it had also been optimized to be good for HDDs, in particular to maximize the I/O bandwidth that you got from HDDs. And so when SSDs, a function of that is that the software architecture is such that it introduces delays which are acceptable for HDDs, but would be disproportionately large compared to device latencies that we were seeing from SSDs. And therefore, the viability of ONTAP as an SSD storage platform was brought into question. Right? There was this question about, can this legacy system do SSDs well? Right? And so we were faced with this challenge, and the work that I'm describing here is part of a multi-year journey that we undertook at NetApp to transform ONTAP into not just a competitive, but we think a class-leading flash storage system. Now, at its core, ONTAP already had a very strong foundation for what SSD systems would look like. In particular, from its inception, it has been a journaling file system that accumulates small random writes in NVRAM and then writing them in large sequential batches to disk, which has a relation to wear management for SSDs. And it already had storage efficiency techniques, compression and dedupe, which have an impact on the economics of SSDs, although at that time we were doing these as batch background jobs. So we had some ingredients, but then we still had to do a number of projects in a variety of areas to make it a good system. In particular, we did some journaling, some work on allocations and matched them up with erase block sizes, so that we could combat the log-on-log problem that was common with SSDs. We made the storage efficiency techniques. Oops, how did that happen? Okay, we made the storage efficiency techniques inline so that we would not get the write amplification effects of doing background jobs. We also introduced new forms of storage efficiency, in particular sub-block compaction, that deals with fragmentation within blocks. Ton of work in the write path optimizations. We changed the scheduler a little bit. So a number of projects, and a lot of that work has already been published in papers that are linked here. But the elephant in the room is read performance, and the rest of this talk is going to be about how we optimize the read path. So a quick primer on the waffle stack, on the ONTAP stack. At the bottom of the stack are storage drivers. There's a layer of RAID software on top of this that assembles all of the devices that it sees into RAID groups and presents pools of blocks to Waffle. Waffle is write anywhere file layout. It's the file system that ONTAP has had since 1992, and it takes these pools of blocks and carves them up into spaces called aggregates and serially numbers blocks from in 4 kilobyte chunks from 1 to n. Within these aggregates are created volumes. Volumes have files, and files are just trees of blocks, as you would expect. And then on top is a protocol stack that has a number of protocol servers for different protocols that allows clients to talk to the core file system layer. Now, the way the software is organized is that each of these layers has its own data structures and its own thread pools. And this simplifies synchronization and allows for independent development of all of those, independent development and optimization of all of those layers. The layers communicate with each other through message passing. And that's good, but it results in a stack that looks, in an I/O path that looks something like this. Right? You get a network request for a read. A protocol handler unpacks that, sends a message to Waffle. Waffle looks at the file ID and the offsets in question, and if the data is already in memory, then we are done. But if the data isn't in memory, it tries to look up some metadata to find the block numbers corresponding to those offsets. So it finds all of those block numbers and sends a request off to RAID. RAID then takes those block numbers and uses its knowledge of the topology to convert them into drive ID and LBA mappings. And then for each drive that's involved in the read, it sends off requests to storage threads that handle it. On the return path, there's a RAID read done message that does integrity checking, verifies checksums, and does corrections if needed, and so on. Sends a Waffle read done message. That message runs in Waffle and is responsible for marking all of the buffers that were just read from disk as valid in memory. And then finally, the Waffle read message runs again. This time, it finds all of the buffers that it was looking for in memory and is able to run to completion, compile a response, and send it off to the client. Now, notice that this Waffle read message, I said it runs again. And this is the artifact of a concept in Waffle called suspend and restart. It's an elegant programming model. What happens is anytime a message handler comes across a resource that is unavailable at that time, it yields, waiting for that resource, and it starts over when the resource becomes available. Right? It's elegant to program with, easy to reason about, avoids deadlocks and such. But it also means that a message handler may run multiple times in order to complete a particular request, and therefore there's a CPU cost to that. So this is where we stood. We took a latency breakdown analysis, and y-axis is latency, x-axis is increasing load, and each bar represents the latency. The components within the bar are like wait times and CPU utilizations at various layers. There are plenty of details about this in the paper, so I won't go into the details of this. But I'll say that we started by trying to attack the wait times at the RAID and the Waffle layers. And so hallway conversations happened, debates happened, and someone said, can we eliminate this read done thing? Do we really need all of this stuff? And so we set about trying to solve that. Quick primer on how the Waffle buffer cache works before we go to the optimization itself. There are two kinds of buffers in Waffle. First, there are file buffers. File buffers are indexed by file ID and offset in terms of 4K blocks. Then there are page headers. Page headers are indexed by aggregate ID and block number. So the page headers own the 4 kilobyte page, which has the contents of the block, and file buffers point to it. Now, because we have things like dedupe and snapshots and clones and things, block numbers can actually be shared by multiple files. And therefore, these pages are multiply referenced. Page headers have reference counts, and they are free to be accessed from any code in the system. File buffers, on the other hand, are managed through a system called Wafinity. We've published about this before. It's a system wherein all of the file system data structures are partitioned, and each is assigned to an affinity. The rule is that only a thread that is owning an affinity at a particular moment in time is allowed to access data structures corresponding to that affinity. And therefore, that limits the execution context, and that's how we get concurrency. But this is also the reason that we had to have this Waffle read done message, because you need to have code running in Waffle to go and change flags on file buffers to mark them as valid, right? So we then started to question that, and we made a few changes to the system. The first change was we moved this concept of validity from the file buffer into the page header. So it's not a file buffer that becomes valid anymore, but a page in memory that becomes valid when a block has been read in. And that, as I said before, is the page header is sort of a MP safe data structure, and so you can do that from any execution context. This looks like a small change, but obviously it has semantic implications all of our code base. Right. The second thing that we did was introduce the concept of an I/O buffer. An I/O buffer is a third kind of buffer. It is like a file buffer. It can be used as a vehicle for I/O. It shares a reference to the page with the file buffer that we're actually trying to read and fill. But it does not have an affiliation with the file, and therefore it's exempt from all of these WAF-inity rules. Right? So then we're able to take an I/O buffer, attach it to a page, and dispatch an I/O and have the page header be marked valid when the I/O is complete. The upshot is that now we can make the RAID read completion handler call some waffle function that is able to say, I have all of these block numbers read in, go mark all of the page headers valid for it. And we don't actually need to execute any code in waffle anymore. So we're able to eliminate that box that I showed earlier. The switching is a little slow. Yeah, we're able to eliminate that block that I showed earlier, and we end up with a situation like this, right? The next thing we realized is that we actually don't even need to come back into waffle in order to fill out the response vector. We already have all the pages that we need. We know what the message, what file offset and length it was interested in, and therefore from RAID code we can make a waffle function call to say fill out a response vector and send it off to the client, right? And so we did that, and so we didn't have to start the waffle read message anymore. That brought us to this state. We were very enthused by the improvements that we already got, so we tried to apply the same techniques to RAID as well. On the request side, RAID goes about looking up its topology cache and doing those translations I talked about. So we actually made the topology cache MP safe accessible from outside RAID under a subset of conditions, only when the topology was stable. And so Waffle could now look up those translations. Some code running in Waffle looks up those translations and finds the mappings and talks directly to the storage thread. On the return path, the storage thread is able to call some API to do the checksum and integrity checks, just verification, not correction, right? And majority of the time, that is all you need. And then the storage thread is therefore then able to reply directly to the client, which gives us a stack that now looks like this, much better, much better. And if you do a latency breakdown analysis now, we were at two different load points. You can see that from the baseline to the succession of fast paths, the latency has substantially improved, right? Throughput versus latency is a better chart as well. X-axis is throughput increasing from left to right, latency is on the y-axis, and you can see that the curve is going down into the right, which is an indication that we are able to get higher throughput at a lower latency at the same kind of utilization, right? There's plenty of details about the methodology and the configurations and things like that in the paper. I'll defer to the paper on that. So overall, the technique that we used was basically to find some majority cases that occur in the code and find an efficient way to execute them without too much context switching or message passing. And that applies a high percentage of the time and accrues a lot of benefit. At the same time, we retained all of the code that already existed that did the careful correctness checking. And so we invoked that path for all of the exceptional cases, like if there was a checksum error or if the topology was changing because someone was adding or removing a disk from the shelf or whatever, right? Now, at about this time, NVMe was becoming the norm. And we were starting to support NVMe devices in the backend and an NVMe protocol in the front end as well. So we needed to, and latencies were in the tens of microseconds now, so we needed to improve the system even more. So we were wondering whether we could eliminate that box in Waffle, that Waffle read message on the request path. And so we went about trying to do that next. To do that, we invented two more data structures. One was called a storage location cache. This is a cache that is MP safe, and it stores mappings from file offsets to block numbers. It does that by maintaining a reference to indirect blocks in the buffer cache, which house those mappings natively. The second data structure is a hierarchical attributes cache. This is a cache that stores some state about volumes and inodes. Is a volume online? Does this user have permission to read those inodes? What is the size of the inode? And things like that. Things that will enable gating checks to let you decide whether to do the read request at all or not, right? The storage location cache also has a bitmap within it. for each of the blocks that is indexed from the indirect block, it maintains a state of whether that block has been modified inside the file system code. And if yes, then it indicates that it's not safe to access from outside anywhere. You have to be inside the waffle domain to read that buffer. Now take these two things, the storage location cache and a hierarchical attribute cache, and then take the two concepts from before. So we said there are page headers that can be accessed from anywhere because you have an MP-safe data structure and they carry validity of things that are in memory. And you have the concept of I/O buffers, which can be used for vehicles for I/O outside of waffle. And so now you can write a read handler, which we did, that is able to look up block numbers, make sure that it's okay to process the read, look up memory to see if it's already there, and if it's not already there, do IOs to get the blocks in memory, and you're able to achieve a path something like this. That unlocks a ton of performance, and that you can see from the chart here. The blue lines represent random reads, which are 4K size random reads. The orange lines are 64K sequential reads. And there are plenty of details in the paper, but I just wanted to give you a flavor of the nature of the improvements that we saw. Right? There are also some interesting and surprising kind of benefits over here. Right? I talked earlier about this concept of waffinity and the fact that data structures have an affinity. Now, as it happens, we limit the number of affinities that are available per volume in the system in waffle, so that we can fairly allocate resources and time in like multi-tenant workloads and such. But what that also means is that, let's say I have only 8 affinities for a volume in my system. It means that the degree of parallelism that I can get for a workload that is only hitting a single volume or a single LUN is 8. Right, and so that was a limitation. However, now we were running code in a protocol thread context. This slim read handler was running in a protocol thread context, and the protocol thread pool is able to dynamically scale up and down based on how much bandwidth is needed to process all of the requests that it's seeing. And so you get opportunities to do much more parallelism for a concentrated workload when you're running in this manner, and you can see dramatic improvements just from the fact that we've unlocked more parallelism. Right. Quick note on correctness. While the slide comes up. So ONTAP is a multi-protocol system, number of protocols supported, and we guarantee the consistency characteristics of the strongest consistency guarantees across all the protocols that we support. Right? And in particular, we talk about 2 behaviors. One is read after write behavior. And this means that any read that comes into the system sees the effects of all writes that have come before. And of course, we can't know that a client has seen our acknowledgement for a particular write before they dispatched a read. But as long as we have dispatched the response to any mutating operation, any read that comes after that will see the effect of those writes, and we guarantee that. Also, the second behavior pertains to concurrent reads and writes, and this says that if there are reads and writes that are occurring that are in flight roughly at the same time in the system, then the read either sees a state before the write or after the write, but never some mix of the two. So essentially, reads are atomic or isolated, right? And there's only I think only some SAN protocols sort of break this above for really large IOs. And these correctness guarantees are not violated by any of the fast paths that we invent. So in the interest of time, I'll skip over these, but basically we make sure for both the RAID and waffle fast paths that I described earlier and the topspin path that I described later, we make sure that these guarantees are always preserved. Okay, so to summarize some lessons that we learned from this. ONTAP had already been built for several years. It's a complex and powerful system with a large volume of software, right? And the strategy of extracting common case code and putting that in a lean and efficient code path while retaining a legacy code path in order to handle all the exceptional and error cases, that's a great way of that's a great strategy to make software efficient in such a system. That worked very well for us. So that's the first observation. A huge part of this is that concept of waffle restart that I talked about earlier. The nice thing about waffle restart is that if you have partial execution and you discover some error or fail in some way, when you restart, you disregard all of those partial execution states and you start on a fresh slate. And so waffle restart makes it very easy to reason about correctness and actually just do the legacy code and get it right after you tried something optimistic and it failed. Right, so that worked out very well for us. The second thing is that because we were already such a feature-rich and trusted system by all of our customers, the approach of doing surgery on the I/O path allowed us to retain all of the features that we were already offering to our customers while improving performance. The alternative would be to build a system from the ground up, but then it would have taken tremendous investment of resources in order to achieve feature parity with ONTAP, right? And so in hindsight, it was a great strategic approach for a system like ONTAP to choose the path of incremental optimization. And maybe legacy is not such a bad word after all. Okay, so I'll conclude with that. Credit to a lot of engineers at NetApp who worked on this over a multi-year period. There are some things that we haven't published yet that are related to this area, and hopefully we'll publish that work in upcoming years. Thank you for your time.